Welcome to Monster Chemistry Review. Ladies and gentlemen of Period 2, AE Chemistry 2014-2015 school year, welcome to this year's Monster Chemistry Review. So, ladies and gentlemen, of my Period 3 Accelerated Enriched Chemistry class, the very last class I'll be seeing for the 2014-15 school year, very sad moment indeed. Welcome to this year's Monster Chemistry Review!
Whoa!
Yeah! Information about the Regents before we leave today. Just to reiterate, the Regents exam will be Tuesday, June 23rd. It is a morning exam, which means it starts at 8 o'clock. Minimum testing time, 10:30. Maximum testing time, 11 o'clock. If you're not done by 11, they just take what you have, so please make sure to budget your time accordingly. All you need to bring with you is a calculator, any kind of calculator, as long as it's not a graphing calculator. Graphing calculators will not be allowed in the room. In addition to blue or black, I would suggest bringing multiple blue or black pens will be required. Pencils can be used on graphs only. I would avoid using pencil on the main part of the test because we've actually had situations where people have forgotten to go back and fill in pen, and 11 o'clock comes and that's the end of that. So please make sure you bring blue or black pens, multiple of them just in case you run out, and a calculator. A simple non-graphing calculator is fine. Math is not going to make or break you on this Regents. Basically it's just, show a correct numerical setup, and almost everything's on reference table T anyway, so it should be fine. What does the potential energy diagram mean? Now, potential energy diagram doesn't really have a meaning per se. What it is a graph that specifies what happens to potential energy during a chemical change. And what it does is it maps out the potential energy, often in kilojoules, over the time that the reaction takes place. Often called the reaction coordinate because it doesn't have any units. Anyway, it starts at reactants, you add activation energy to get the reaction started, and then it forms your products. So wherever you start is your heat of reactants, wherever you end is called your heat of products, and the difference between them is called the delta H, or the heat of reaction. Now, as far as the rest of this is concerned, in order for a chemical change to take place, the reacting particles have to collide, and they have to collide effectively with enough energy and at the correct angle. If they don't, they'll just bounce right off each other. So, why do they have to hit each other? Before you can get a chemical reaction to take place, you have to break any old bonds that you have. So the first part of this, the activation energy, is added to break any old bonds that you might have. Then once you reach the activated complex, new bonds can start to form. And that's what the down part of this PE diagram is all about. New bonds formed. Now, in this particular case, less energy is needed to break old bonds than we get back when new bonds are formed. So there's an overall decrease in potential energy, a negative delta H, making this an exothermic PE diagram. And if you go to reference table I, this would be the potential energy diagram for any of the reactions on reference table I that have a negative delta H value. And at the bottom of table I, it will tell you that a minus sign indicates an exothermic reaction. And that's essentially what potential energy diagrams are all about. The difference between esterification and etherification. If we take a look at reference table R. Reference table R gives us esters, and I have to back it up a little bit to get to ethers. There we go. Esters and ethers. Ethers have a single oxygen between two carbon chains, and esters have a carbon double bonded to one oxygen and single bonded to another oxygen in between two carbon chains. So ethers have one oxygen and esters have two oxygens. So the reactions that produce them are similar, yet different. They both form through a process called dehydration synthesis, putting two molecules together to form a bigger molecule. Now, it's often easier to work backwards. For example, if I've got methyl ethyl ether, how did we get it? We reacted together methanol and ethanol. During this change, one of the hydrogens from this alcohol is removed, the hydroxyl group of the other alcohol is removed, using a catalyst, most often sulfuric acid, which is great at dehydrating anything. This gets pulled off and forms water. And since an ether is formed, this process is called etherification, because you make an ether. To make an ester is a very similar process, except let's say we wanted to make ethyl methanoate. We would need methanoic acid as the source of the COO that goes in the middle of the molecule, and we would need ethanol. Again, with a sulfuric acid catalyst, the H is pulled from the acid, the OH is pulled from the alcohol to form H2O. That's why it's called dehydration synthesis. When this happens, the molecules join together where the H and OH were, giving you an ester. And because this is an ester, it's known as esterification. And that's the difference between them. Etherification makes an ether by dehydrating two alcohols, whereas an ester is made by dehydrating an alcohol and an organic acid. How do you do double replacement? I don't know, is it a dance? Actually, that's actually pretty good. It is a dance. It's a dance between ions, for example, sodium chloride, reacted with silver nitrate. Dissolve them in water to break them up into ions. Mix all the ions together in a container, and the Na and the NO3 will remain dissolved. Why? According to reference table F, any compound with either sodium or nitrate is soluble in water and remains broken up as ions as an electrolyte. However, silver and chloride come together. Chloride is soluble except when combined with silver. So it falls out of the solution as a precipitate. So we take a beaker, we mix the two liquids together, the two aqueous solutions together, and then you start to see particles of silver nitrate form, fall out, and settle to the bottom as a precipitate. How does particle size affect intermolecular attractive forces? Excellent. Okay. The only type of attractive force you need to know the name of is hydrogen bond. And there, the only thing that's important is that you've got H on one side, N or F on the other. And let's say we've got HCl, H2O, and HF. And it asks you which has got the strongest attractive forces. What you'd have to do is look up the electronegativities of the atoms that are bonded to the hydrogen, and then see which one of them gives you the highest END. And that'll tell you which one is the most polar. Because fluorine's got the highest electronegativity, fluorine's always going to give you the strongest hydrogen bond attractions. But that's not what the question is asking. The question is asking, how do particle size affect attractive forces? This works with London dispersion forces, which are not testable on the Regents by name. Let's suppose we have helium, neon, argon, krypton, and radon, and we compare their atomic radii. It's the easiest way to explain because, where are we? Because they're monatomic. So let's see. Helium has a radius of 37 picometers. Neon has a radius of 62. Argon has a radius of 101. Krypton has a radius of, it's off the charts. Here we go. Krypton is 116. I think you can see where this is going. As you go from the top to the bottom of the periodic table, atomic radius increases. And what this means is that you also have increasing intermolecular attractive force strain. So essentially, the bigger your nonpolar molecule is, the stronger the intermolecular attractive forces will be. Taking that a step further, if we compare the alkanes, methane, ethane, propane, as the size of the molecule increases, the attractive force strength increases as well. Methane is a gas at room temperature and room pressure. Ethane is also a gas. Propane is a gas, but with enough pressure you can liquefy it, because its attractive forces are stronger. You do need a pretty sturdy tank to do it though. Butane is a gas at room temperature, but it only requires a tiny bit of pressure to turn it into a liquid. Lots of pressure to liquefy it, very little pressure to liquefy it. So as molecular size increases, so do attractive force strength. So bigger molecules will have stronger attractive forces. This applies specifically to nonpolar molecules. How can I detect changes in entropy and enthalpy? Okay, we'll start with enthalpy. When I let go of this, which way does it go? Down. Nature favors a decrease in overall energy. Enthalpy is that energy. So a negative delta H would be an example of a change in enthalpy. And again, if you want to find out what the change in heat is for various changes, all you have to do is go to reference table I and look it up. You want the heat of combustion? Here we go, first 6 reactions. Heat of formation, also known as heat of synthesis, that's the next batch of reactions. Heat of dissolving, heat of solution, that's the next batch. And then heat of neutralization would be the last one. Negative would be exothermic, positive would be endothermic. And that's how you can detect changes in enthalpy. Entropy is based on phase. Solid to liquid to gas is increasing in entropy, because entropy is a system state of disorder. So if we have H2O liquid turns into H2O gas, what's happening to the entropy? It's increasing, exactly. If we have Na solid plus Cl2 gas forms NaCl solid, what's happening to entropy over the course of this reaction? Right, we start with a solid and gas, but we end with all solid. So this would be decreasing entropy. And so that's how you can determine the changes in entropy, based on the phase that you've got. Going up in phase, you're increasing entropy because things are getting more, that was a terrible example. Imagine if I took this beaker and dropped it. Not only would you have a decrease in energy, but what would happen to the glass when it hit the table? Right, that would be an increase in entropy. So if you ever want to know what nature favors, just picture knocking a glass off a table onto a concrete floor. And that's what nature favors. Lazy, because energy drops, and messy, shards of glass everywhere. So make sure you're wearing, sturdy shoes so you don't puncture your feet, because that's just awful. Okay. Can you review the math problems Q equals MC delta T? So if we take a look at reference table T, you'll notice under heat they give us the equation where Q is heat, M is the mass of water that you're heating up in the calorimeter, C is the specific heat capacity of that water, which is always 4.18 joules per gram Kelvin or degrees Celsius, doesn't matter which one you use. And delta T represents the change in temperature. Now the question that I got most often on the Regents review looked something like this. If 800 joules of heat are added to 10.0 grams of H2O at, let's say, 20 degrees Celsius, what will the new temperature be? This was the one that came across most often. Do you guys recognize this? Okay, so we're trying to solve for the new temperature, so we need to solve for delta T. So we'll divide both sides by MC. So let's see, we plug that in. Q is 800 joules over the mass is 10 grams times the specific heat is 4.18 joules per gram degrees Celsius. Joules cancels, grams cancels. And what does this give us? Handy dandy calculator, please help us. So that's 800 divided by parentheses 10 times 4.18 and parentheses equals 19. And let's see, 3 sig figs, 19.1 degrees Celsius. But that's not our answer. This is how much the temperature changes by. If we're adding the heat to the water, and the water starts at 20 degrees, and this is how much the temperature of the water goes up by since we're adding heat to the water, what's our new temperature? Right. 39.1 degrees Celsius will be our new temperature. It's probably one of the more common ways you're going to see MC delta T used on a Regents exam. What is the best way to determine what type of bonding is present? This comes down to what elements you have. And it can very simply be described thusly. If you bond a metal to a nonmetal, it's ionic. Metals form positive ions, nonmetals form negative ions, opposite charges attract. If you bond two nonmetals together, and that includes hydrogen, you get a covalent bond, where the electrons are shared. One pair of electrons are shared to make a covalent bond. By the way, this is all in an attempt for every atom to form a stable octet. Metals will lose their outermost electrons, and there's a stable octet waiting underneath. Nonmetals will gain enough electrons to form a stable octet. Ionic bonds form. Okay, somebody's getting murdered apparently. Metals will lose their electrons to form positive ions. Nonmetals will gain them to form negative ions. That's how they make stable octets. Nonmetals can't both gain, they have to share, and they share in such a way that they end up with a stable octet. So for example, if we've got sodium, which has a configuration of 281, one valence electron, and let's say fluorine, which is 2-7, has 7 valence electrons. The sodium has an electronegativity of let's see. I keep changing this on these tables, so I think it's 0.9. We'll just verify. Yeah, 0.9. And fluorine is the bad boy of the periodic table at 4.0. That's an electronegativity difference of 3.1. If it's greater than 1.7, in general, it's ionic. And what that means is that the metal loses its outermost electron, making a stable octet. The nonmetal will gain that electron, making a stable octet. The fluorine becomes a negative fluoride ion. The sodium becomes a positive sodium ion. And that's how ionic bonds form. The way a covalent bond will form, we have a bond between hydrogen, and it has 1 valence electron, the only electron that it has. Chlorine has 7 valence electrons. It has a configuration of 2-8-7. Hydrogen's electronegativity is 2.2. Chlorine's is 3.2 for a difference of 1.0. If it's less than 1.7, typically it's a covalent bond. And in this case, because it's above, because it's between 0.5 to 1.7, that would make it a polar covalent bond, where the electrons are being shared unevenly. Now they both can't gain, so what happens is the H just simply says, all right, tell you what, I'll share my electrons with you so that you can now have a stable octet, and me, I've got a stable, well, I only have 1 energy level, so a stable duet. And they live happily ever after until someone adds enough activation energy to break old bonds, which requires absorbing energy. Lots of energy, because covalent bonds are very tough. One last kind of bond that goes forgotten very frequently is not a bond that forms compounds. It's a bond that forms solid metals. Solid metal! All the metals on the periodic table, the only way the atoms can stay together, like in this chunk of aluminum right here, is through what's called metallic bonding, which is a combination of both losing and gaining electrons and sharing electrons. And that's what allows electrons to freely move through a metal that allows it to conduct electricity. You can't make compounds out of metallic bonding, but metallic bonding is what holds metal atoms together to make solid metal. And it also is what allows metals to be malleable and ductile, gives them their properties. What mathematical expression represents the heat of reaction? This is just a vocabulary term, and it's not on reference table T.
That one's mine.
Heat of reaction is defined as the heat of the products minus the heat of reactants. And the reason this works is, let's say again, little potential energy diagram. Let's say the heat of reactants is 70 kilojoules. And the heat of the products is 20 kilojoules. Our heat of reaction, or delta H, would be 20 minus 70. What would that give us? 50. Not 50. Negative 50. Which we can verify on the diagram because the total amount of energy goes down by 50. And that's why it's products minus reactants. That way we get the correct sign for delta H. Oxidation numbers. Not exactly a question, but I'll answer it anyway. Oxidation numbers are the charges that appear on your periodic table. In fact, it's labeled in the key as selected oxidation states. Some elements only have one possible charge, others have multiple. So let's see how this works. If we've got Na and NO3, and we want to find the ion charges, that's easy. Sodium is only ever +1. And we can get the charge of the nitrate ion simply by going to reference table E. The nitrate ion has a -1 charge. But what if we wanted to dive deeper than that? What if we wanted to find the charge of the nitrogen? Well, in order to do that, we have to do a little bit of mathematical gymnastics. Sodium contributes +1 to the total charge of this compound. Each oxygen is -2. There's 3 of them for a total of -6. So for this whole thing to add up to 0, because all compounds are electrically neutral, what does nitrogen have to be to make this all add up to 0? We have +1, we have -6. What do we need to make this all add up to 0?
5.
Say again?
5.
5 plus or minus?
Plus.
Right, +5. Here's another tip for the Regents. You've got to put the sign of the charge. You can't just put the number. It's either positive or negative. I had a student who missed getting 100 on the Regents. And if you're watching, I'm sorry, I'm not mentioning you by name. They missed getting 100 on the Regents because they were asked, what is the negative ion? Identify the negative ion in nitric acid. Well, that's easy enough. You can just look up nitric acid on the common acids table. Nitric acid is HNO3. So what did they write as their answer? What is the negative ion? They wrote this. And that cost them getting 100. Yeah. You wouldn't need parentheses. We wouldn't take points off if you did put parentheses. Got to make sure you have the symbol and the size of the charge. The magnitude and direction, positive or negative. Any other questions related to this? Yeah.
Will there ever be a question where including the charge will make it incorrect?
If they ask you for the oxidation number, what's the charge of Na?
+1.
You would get it incorrect. Because if Na is not in a compound, what's its charge? 0. So that would be the situation where if you put a plus or minus, it would be incorrect. So elements that are not part of a compound, you may have misunderstood the way I asked the question, but Na by itself, when it's not in the compound, has no charge. And that's an example of when you would get it wrong if you did put a charge. In fact, if it's 0, you don't have to write anything. In fact, often they'll just say Na and they mean Na0, because any element by itself has a 0 charge. Why? Sodium has an atomic number of 11, a configuration of 2-8-1, that's 11 electrons, 11 protons, has no charge. Explain how to write compounds. Now, I'm not sure if whoever wrote this meant how to write the formulas, the names, the dot diagrams, or the structures. So we'll do them all. Let's say we had iron 3 sulfate, and we wanted to write the formula of it. They do you a favor by saying iron 3 here, because iron can be, Gesundheit, iron can be either +2 or +3. So by saying iron 3, they're telling us that it's the +3 variety of iron. As far as sulfate is concerned, that's easy enough to find. We just have to look that up on table E. Sulfate is SO4 - 2. And then it's just a simple case of, what is it? Drop and swap, drop and swap. Just cross over the charge on top. And there's your formula. So that's the name, that's the formula. 2 times +3 is +6. 3 times -2 is -6. The charges cancel out. We know that's a proper formula. Now, as far as dot diagrams are concerned, let's suppose we're going to just do simple ones. Let's say we want the dot diagram for magnesium fluoride. Magnesium is Mg, and it has a charge of +2 when it's in a compound. Fluorine is F. Be very careful about this. I've had people lose points because they wrote the symbol of fluorine as being Fl. And that's the symbol of fluorovium, not the symbol of fluorine. So fluorine is just F. And if you ever run into any question about what the symbol is, all you got to do is look it up on table S. Fluorine is F. And it has a charge of -1. And that's the only charge it can form. So, based on drop and swap, what's the formula for magnesium fluoride? MgF2. Okay. Now, to write the dot diagram, the metal has lost all of its valence electrons. Therefore, it has none. So you would draw none. That would be the dot diagram for the magnesium ion. We have two fluoride ions that are -1. They will go on either side of where the magnesium is. Because they're -1, they repel each other, but they're both attracted to the magnesium. Fluorine has a configuration of 2-7. To become -1, it gains an electron. It now has 8 valence electrons. All nonmetal ions, with the exception of hydrogen, because it only has 1 electron to start with, has a stable octet. And that would be how to draw the dot diagram for an ionic compound. Writing compounds with Roman numerals. I'll do another example. Let's say we have CuCO3 and Cu2CO3. This is copper carbonate. You can find out that it's carbonate because if we take a look at table E, CO3 is the carbonate ion. This is also copper carbonate. Now I'm going to relate this to, let's say, oops. This is 4 carbons with a double bond. This is butene. And this is also 4 carbons with a double bond between them. This is also butene. But they're all obviously different substances. So we have to have a way of differentiating between them. And the way that the International Union of Pure and Applied Chemistry has decided this will work is we'll find the charges of these ions. Carbonate is -2. That means copper has to be +2 to cancel it out. Here, drop and swap tells us that this copper is +1 because we only have 1 carbonate. So what we do is we write the Roman numeral to represent what the charge is as part of the name. This is copper carbonate made from the copper +2 ion. This is copper carbonate made from the copper +1 ion. How do we do it for organic compounds? How many carbons in before we get to the double bond? This is 2 butene. This is 1 butene. So the International Union of Pure and Applied Chemistry has come up with a very sophisticated and simple naming system to help you distinguish between compounds that would otherwise have exactly the same name. By the way, when you see the term IUPAC on your Regents, it just means the naming system that you learned in class. How do you tell the difference between equations for transmutation, fusion, and fission? Well, fusion and fission are forms of transmutation. In fact, every single nuclear reaction that you have is transmutation. Transmutation literally means taking one element and turning it into another. It could be natural decay. 14/6C turns into 14/7N by vomiting out an alpha particle. This would be natural transmutation because carbon is turning into nitrogen and one element is turning into another and spontaneously vomiting out a decay particle. Artificial transmutation, 239.94 Pu plus 4/2 He forms 242/96 that's curium. Curium plus a neutron. This is artificial transmutation. And the way we can tell it's artificial is, in natural, carbon turns into nitrogen all by itself. We don't have to hit it with anything. In artificial, plutonium turns into curium, but only if we whack it with an alpha particle. So that's the difference between natural and artificial. In artificial, you have to hit your particle with another particle in order to turn it into a different element. Now, fission is a form of artificial transmutation. It's something we don't see occurring in nature at all. And an example of, and there's many different examples of fission, 238 over 92U, hit it with a neutron. That's why it's artificial. Uranium-238 won't undergo fission unless you hit it with a particle. Turns into 92 over 36 Ku, Kr rather, plus 141 over 56 Ba, plus 3 neutrons. This is only one example. There's many different ways that uranium actually splits apart. This is just kind of like one way that uranium can be split apart. And because you're turning one nucleus into two smaller nuclei, that would be an example of fission. And finally, if you've got two hydrogen atoms, specifically deuterium works really well, but you can also use tritium. You're fusing the hydrogens together to make your new element. So that would be fusion. And this does happen naturally. This happens in the center of stars. And we've been able to figure out how to make it here on Earth. The advantage to fusion is that it generates a lot more energy per gram of fuel. The advantage of fission is we have the technology to do it right now. The disadvantage of fission is that it produces radioactive byproducts that we have not yet figured out how to deal with in terms of long-term storage. An example of balancing an equation. There are two kinds of equations that we can balance. Thank you. First kind of equation is just straight up. Like, let's say we have Na plus Al2SO4 3 forms Na2SO4 plus Al. Nice little single replacement reaction. To balance it, we have to make sure we have the same number of either elements or ions on both sides. So in this case, we've got one sodium on the left, we've got two on the right, so we put a 2 in front to balance that. That might change, don't know yet. We have 2 aluminums on the left, only 1 on the right, so we put a 2 in front of that. We have 3 sulfates on the left, 1 sulfate on the right, so we put a 3 in front of that. Oh, but that messes up sodium. Now we have 6 sodiums, we go back and revise sodium to 6. And it's really easy to double check. 6 sodiums, 2 aluminums, 3 sulfates, 6 sulfate, okay, 6 sodiums, 6 sodiums, 2 aluminums, 2 aluminums, 3 sulfates, 3 sulfates, we're good to go. Then instead of giving you the sulfate ion, let's say instead of giving you aluminum sulfate, they just give you aluminum plus 3. Let's say instead of giving you sodium sulfate, they just give you sodium plus 1. And you have to balance it. And you look at it and say, it's already balanced. It's not. Law of conservation of mass is obeyed, but the law of conservation of what is being flagrantly violated here? Charge. Yeah. We got plus 3 on the left and plus 1 on the right. How do we do that? Simple. How much is aluminum changing charge by? Put a 3 in front of the other thing, sodium. Now sodium is also changing by 3. How much does sodium change by? Each sodium change by? 1. Put a 1 in front of the aluminum. Now we've got plus 3 on the left, we've got plus 3 on the right. 3 times plus 1 is plus 3. 3 sodiums, 3 sodiums, 1 aluminum, 1 aluminum. Bing, bang, boom, done. Difference between electrolytic and voltaic cells. I want to show them side by side. Voltaic is spontaneous. All you got to do is plug it in, flick a switch, and it starts providing electricity. Electrolytic is non-spontaneous. It will not happen without an outside source of power, like a voltaic cell. Voltaic cells take chemical energy and convert it into electrical energy. Electrolytic cells take electrical energy and make a chemical change happen as a result. Batteries, voltaic cells, are used as a source of direct current. Electrolytic cells use direct current to make either decomposition or electroplating happen. And those are the major differences between them from a functional standpoint. Sketching them out. Voltaic cells are comprised of two half cells. Electrolysis takes place in a single container. Voltaic cells have a salt bridge. Electrolytic cells do not. Voltaic cells have two electrodes. One electrode being made of a more active metal, the other a less active metal, such as zinc and copper. Zinc is more active than copper. There are two electrodes in electrolysis as well, but they are not made of metals. Typically they're made of graphite. And they're not part of the reaction. They're catalysts. The zinc and the copper are dissolved in solution. Zinc nitrate, for example, over here, and copper 2 nitrate in solution over here. Electrolytic cells, there are no solutions. In order to decompose a compound like salt, you actually have to heat it up until it liquefies, pure liquid, not aqueous. Voltaic cells use the electricity that it creates to power a device called a load. Electrolytic cells are the load and require a source of direct current, a battery or voltaic cell, in order to operate. This can power that if the voltage is high enough. So from a diagrammic standpoint, that's how these two differ. The last way in which they differ comes down to charges, anodes, and cathodes. The more active metal is always the negative anode of the battery. The less active metal is always the positive cathode of the battery. You start at the anode, electrons are lost there and go through the wire, and through the load on fire they enter the cathode and reduce the cations, and the anions go through the salt bridge back to where. However, be careful with that song. The anions are not the only thing in motion here. The anions go through the salt bridge to the anode, the cations go through the salt bridge towards the cathode. And in this way, the salt bridge helps to maintain electrical neutrality, complete the circuit of your cell. In electrolytic cells, the battery determines the charge and direction of electrons and the anode and the cathode. A battery has a negative end and a positive end. Anything you hook up to the negative end of the battery is still the negative end of the battery. Anything you hook up to the positive end of the battery is still the positive end of the battery. The direction of electrons is determined. The negative end of the battery is where electrons come from. So electrons leave the negative end of the battery and enter the positive end of the battery. Electrons always go from anode to cathode. Electrons always go from anode to cathode. Electrons always go from anode to cathode. Say that louder.
If that's the case, why is the cathode electrode negative and not positive?
Okay, once again, positive and negative is determined by the battery, and only the battery. Anything hooked up to the negative electrode of the battery is still the negative electrode of the battery. So positive and negative have to do with the battery. Exactly. Anode and cathode have to do with what direction are the electrons going. If it makes it easier to remember, whatever the charge the anode and cathode are in a battery, they're exactly the opposite charge in an electrolytic cell. Exactly the opposite sign. A battery produces electric current. An electrolytic cell will decompose a compound back into its original elements. Here, Na+1 will be given an electron from the battery and turn into solid sodium, which you can then gather off of the electrode. The chloride goes to the positive electrode, where it has its electrons stripped back into the battery. So because reduction takes place here, reduction takes place at the cathode, and oxidation takes place here, anox. And that's another explanation for why they are the signs they are.
You should do the electron metaphor for the video.
Oh, the one where it's like connected beads.
Yeah.
Okay, that's a good point. The wire is not a hollow tube that electrons just pass through. The wire is made of metal atoms, all of which have electrons, and those electrons are constantly in motion. What the battery does is pushes the electrons in the wire through the wire and into the cathode. So if you'll imagine that these are the electrons that are already in the wire, all the battery does is, as it pushes one electron out, it pushes all the electrons forward until this electron gets pushed into the copper electrode. So what's happening here is the battery determines the direction the electrons will go. The more active metal will give up electrons that will push electrons out. The less active metal ion will pull the electrons in, as if the electrons were nothing more than a string of connected beads, where you pull on the beads on this side and they come off of that side. And this is one reason why the zinc electrode gets smaller over time. As the copper +2 pulls electrons through the wire, the zinc gives them up and dissolves into solution. And why the copper electrode gets bigger over time, because as the electrons are pulled into this electrode, the copper +2 ions pick them up and turn into solid copper as they gain them. Continuing the process until either you've used up all your zinc or you've used up all your copper ions and the battery dies. And that's the difference between voltaic and electrolytic. Did this help? Is this what you were looking for? Whose question was this? Go ahead, you're first.
Does the anode go under oxidation in the electrolytic as well?
Always, it's an, ox, and red cat. Oh, and there's another thing too that you can use to remember. The cathode gets bigger, so people can remember that with fat cat. The cathode gets fatter as the reaction goes on. And how can you remember that the anode gets smaller? Remember, it's anox. Skinny cow. Fat cat and skinny cow tells you that the ox gets smaller and that the cat gets fatter as the reaction goes on. So those are just two additional mnemonics that you can use.
How does electroplating work again?
The way electroplating works is very similar to this. The difference is what your ingredients are. In electroplating, you're trying to coat one metal onto another metal. And the thing is, the trick is that the metal that you're trying to plate always has to be hooked up to the negative end of the battery. Like, let's say we want to take a plain old metal cat statue and plate it with silver. So we have a silver-plated cat statue. What you do is you hook the silver metal bar up to the positive end of the battery. The battery will strip electrons from the silver, dissolving the silver into a silver nitrate solution. The object you're plating will always be hooked up to the negative end of the battery. So here's what happens. As electrons pull off of the silver and the silver dissolves, the electrons are given to the metal statue. Now, the metal doesn't want them, so the statue becomes negatively charged, attracting the positive ions. As soon as the positive ions touch the statue, they gain the electrons and turn into a nice thin coat of silver, which for some reason I'm drawing as red. And the thicker the coat, the longer you let it run. Yep, and that's electroplating.
Red.
And again, it's still a load making use of the electricity being given off by the battery. Anything else related to this or anything else? Yeah.
In a supersaturated solution,
Yeah.
does that mean that it is now a heterogeneous mixture?
Yes. Yes. The actual definition of supersaturated and true supersaturated solutions are actually fairly rare. If you've ever made rock candy, everybody here make rock candy? Yeah. What happens is basically you make a saturated solution of sugar at a very high temperature. So you saturate the water with sugar at a high temperature. Now when you lower the temperature, the excess sugar should precipitate, but it doesn't. Sugar is one of those rare substances that remains saturated even when you lower the temperature. But it's a very precarious position. It's very unstable. If you drop so much as one little crystal of sugar into it, all of the sugar that should have precipitated will immediately precipitate. So what happens is you place a string into it. Maybe you coat the string in little crystals of sugar. And as the sugar cools, it will crystallize onto the string and make a big chunk of rock crystal candy. Yeah.
So it needs like a nuclei to catch on.
Exactly, just like raindrops need dust to gather on. Exactly. What we've called supersaturated is really saturated plus precipitate. So what happens is, let's suppose we're at 30 degrees Celsius and we've got 60 grams of potassium nitrate. At 30 degrees Celsius, only 48 grams of potassium nitrate can dissolve. So those extra 12 grams will settle to the bottom as a precipitate. These 48 grams will be a homogeneous mixture, but adding those extra 12 grams of solid onto it makes it heterogeneous. So absolutely, what we call supersaturated is a heterogeneous mixture. How do you find activation energy? This is a potential energy diagram. And on the potential energy diagram, you start at the heat of reactants and you end at the heat of the products. The activation energy is simply the amount of energy you have to give the reactants to get the reaction to go. When two reacting particles want to react, they first have to collide. And they have to collide effectively. They have to collide with enough energy, and they have to collide at the correct angle. Otherwise, they'll just bounce off each other. Why do they need activation energy? Before a reaction can take place, any old bonds need to be broken. Got to break old bonds before you start making new ones. And that requires adding energy, and we call that activation energy. Then, on the other side of the PE diagram is when new bonds form. Now, in this particular case, less energy is needed to break bonds than we get back when we form new bonds. As a result, our heat of reaction, or delta H, is going to be negative. Why? Heat of reaction is equal to the heat of the is equal to the heat of the products minus the heat of the reactants. Now, let's say the products had 20 kilojoules stored and the reactants had 50 kilojoules stored. The products are 20, the reactants are 50. What is our heat of reaction? Negative 30. Heat of reaction is also known as delta H. So that's what activation and energy is. It's the energy you have to give the reactants to break old bonds before the atoms can rearrange and form new bonds. That's a potential energy diagram. How do you determine which substance is an electrolyte? Excellent. What is an electrolyte? There are a couple of things that can carry electrical charge. First and foremost, we have metals. Metals are the elements on the periodic table to the left of the zigzag line, not including hydrogen. Metals have what are called metallic bonds, and what happens there is the atoms are simply just passing their electrons back and forth, which means if you push electrons in from one direction, those electrons will keep getting pushed in that direction to create an electrical current. But metals are not the only thing that can conduct electricity. Solutions can conduct electricity if there are charged particles in it. For example, if we take salt, NaCl, and dissolve it in water, it'll break up into sodium ions and chloride ions. And since they're electrically charged, they can carry electrical charge with them. Because when they're dissolved in water, they're free to move around. Acids also dissociate when dissolved in water to form ions. They're the only covalently bonded substances that can ionize when you put them in water. And not all of them ionize completely. Bases are ionic compounds that contain a metal plus a hydroxide. When you dissolve that in water, it also breaks up into ions. And those ions are capable of carrying electrical charge. These are electrolytes. Now on the Regents, when they ask which of the following is an electrolyte, typically they're going to give you a whole bunch of stuff that ends in OH. But only one of them is going to be a base, or an acid. They might give you 3 alcohols that all end in OH, but those are carbon and hydroxide. That's a covalent bond. Bases are metal hydroxides. Alcohols, it's covalent bonded, so the sucker's not a base. Methane all evaporates real quick, it leaves no trace. So typically, the electrolytes they're going to choose are going to be one of your metal hydroxides, or acetic acid is the most common one they ask for. Because it ends, if you read it like this, it ends in OH, just like all the alcohols do. But being an organic acid, it does ionize when you put it in water and allows you to conduct electricity. So if they ask you which of the following is an electrolyte, typically it's going to be something on table K or something on table L. So go right to those tables. Same thing if they say which of the following yields OH minus as the only negative ion in solution, or which one ionizes in water to yield H plus as the only positive ion solution? Tables K and L. Don't forget, because they're very, very handy. Okay, any other questions relating to that? Yeah.
So it's H3O, is that like a positive?
H3O the hydronium ion is what happens when an acid dissolves in water. The H from the acid combines with the water to form H3O plus. So they'll use H plus and H3O plus interchangeably. So when they mention a hydronium, they're talking about an acid. And when they talk about hydronium and pH, for example, pH of 1, 2, 3, 4, 5, a pH of 1 is 10 times stronger. pH of 1 is 10 times stronger than a pH of 2. Yeah, going from a pH of 3 to a pH of 1 would be 100 times stronger. Going from a pH of 4 to a pH of 1 would be 1,000 times stronger in hydronium ion strength. Yep. There's my graphite. Look at that graphite. Remember the question on the Regents that said graphite and diamond, do they have similar properties, different properties? Does this look like a diamond to you? It's soft. Here, check it out, right? Blank piece of paper. Can you do that with a diamond? I hope not. Because if you can do that with a diamond, get your money back and bring a cop with you. Yeah, diamond and graphite are both made of carbon, but they're both completely different because their structures are different and therefore their properties are different. So that tends to crop up from time to time. So now I got it all over my fingers. That's it. Explain exo and endothermic, including PE diagrams. Okay, I've already done PE diagrams, but just real quick to show the difference between exo and endo. Exo and endo. A common question will be to sketch the shape of an endothermic diagram or an exothermic. Sometimes they'll even start you off with a little line, and then people don't know what to do with that. That's where they want you to start your graph. So if it starts high and ends low, that's exo. If it starts low and ends high, it's endo. And please don't just put like a slash like that. Remember your activation energy, the highest point on the table, the heat of the activated complex. And that's the difference between exo and endo PE diagrams. How does stress shift changing concentration work? Good, Le Chatelier's principle. Awesome. My favorite reaction, N2 gas plus 3H2 gas forms an equilibrium with 2NH3 gas plus heat. The reason this system is in equilibrium is because what's true of the rate of the forward reaction and the rate of the reverse reaction? They're equal. Exactly. Which means that over time their concentrations will remain constant. For every N2 that you use up, one N2 is made. For every H2 you use up, an H2 is made. So over time the concentrations remain constant. This has to take place in a closed system. Because if you let anything out, then the reverse reaction can't take place. Now, what if we add H2? If we add H2, we're going to have more collisions between H2 and N2 than we had before. This will make the forward reaction go faster. Another way to look at it is, we've stressed the equilibrium by adding hydrogen. It wants to bring the concentration of hydrogen back down. To do that, it has to use up that extra hydrogen, so it shifts forward. As a result, N2 goes down, because you can't use up hydrogen without using up nitrogen, and you can't use up reactants without making more products. and the equilibrium will shift in the direction that will bring you back to your equilibrium once it's done with the shift. Stress, shift, change in concentration. Let's say we remove. The same thing will happen. If we remove heat, if we take heat away, the equilibrium is going to shift in the direction to bring it back. If you cool it down, the equilibrium will shift in the direction, the exothermic direction, that'll bring the temperature back up again. With the same exact results for changing concentration. If you shift forward, your reactants turn into products. If you shift in reverse, your products turn into reactants. Okay? Does anybody want me to take it further than that? I'll just do one more thing. Pressure. If we increase the pressure, the equilibrium will try to bring the pressure back down by shifting to the side that has less moles of gas on it. How many total combined moles of gas do we have on the left? 4. And on the right? 2. So the equilibrium will shift forward to bring the pressure back down again. Towards whichever side has less gas exerts less pressure and brings you back to equilibrium. How to tell when the radius of an atom or period is increasing or decreasing. If you want to find out the trends in radius, like between, let's say, sodium and chlorine, all you have to do is go to reference table S and look up the radius of sodium and chlorine. Sodium's radius, here we go. Sodium is 160. Chlorine is, there you go, 100. So what's happening to radius as you go from sodium to chlorine? Decreases. What about if you go from chlorine to iodine? Well, iodine has a radius of, here we go, iodine, 136. So what happens to radius as you go from chlorine to iodine? Increases. All you have to do is look up the element on either side, as it says, what is a general trend in atomic radius as one considers the elements from sodium to chlorine in order of an increasing atomic number? That's how they'll ask the question. And I just threw my pen. So just look up the radius on the table. Now, if they ask about ionic radius, sodium has an electron configuration of 281. When sodium becomes a +1 ion, how does it do that? So it becomes 2-8. Will its radius be equal to, greater than, or less than 160? Because when sodium loses an energy level, it gets smaller. So positive ions are smaller than the original atom from whence they came. On the other hand, chlorine had a radius of 100. Has a configuration of 287. Ladies in the back? A few years ago I posted a video where there was a huge amount of chatter over what I was doing, and all the comments in the section YouTube said, I can't believe how rude your students are. I don't want the same thing to happen. So if you're putting down comments, don't say that. It's just hot and humid here, it's hard to stay focused. Okay, 287. Guys, when chlorine forms a Cl-1 ion, what does its electron configuration become? (288). It gains an electron. Will its radius be greater than, less than, or the same as 100? Greater than. Because the atom is going to get bigger as it gains an extra electron. Okay. Sweet. Oh, and by the way, the electron configurations of our ions are the same electron configurations that you'll find with noble gases. For example, when sodium forms an ion, it has the same configuration as neon. And when chlorine forms an ion, it has the same configuration as argon. That shows up a lot on the Regents too. Potential energy diagrams plus reverse reactions. Well, we've done potential energy diagrams with 2 questions. Let's take a look at the one thing that they'll ask. What is the activation energy for the reverse reaction? A PE diagram assumes that your reaction is going forward from time 0 to the end. You're going to start here, give it activation energy, and then you'll form your products. Well, to reverse this reaction, you would make this time 0, and you would make this the end. You'd reverse it, which means this now becomes the activation energy for the reverse change. So this would be the activation energy if we were going forward. This would be the activation energy if we're going in reverse. And that's the only thing we really hadn't talked about when we did potential energy diagrams. Oh, one other thing. If you add a catalyst, what does that do? Right, and only the activation energy. It doesn't touch the heat of the reactants. It doesn't touch the heat of the products. You may have noticed when you took the practice Regents, you see the question over and over again, what is the function of a catalyst? What does a catalyst do? It lowers activation energy, removes steps from the mechanism, or creates an alternate reaction pathway, which I don't particularly care for as an answer, even though the Regents accepts it, because inhibitors also provide an alternate reaction pathway. It's just that catalysts have a shorter pathway and inhibitors have a longer pathway. Okay, less time to get there because it takes less energy. What does empirical formula mean? Water has a molecular formula of H2O. That's because a molecule of water contains 2 hydrogens and 1 oxygen. However, this is not just a molecular formula, it's also an empirical formula. Why? Because you can't simplify it any further. Ethane is a molecule with 2 carbons and 6 hydrogens. C2H6. That's a molecular formula. But it is not an empirical formula. To get the empirical formula, you simply have to simplify. CH3 would be its empirical formula. And that's the difference between an empirical formula and a molecular formula. The molecular formula tells you how many atoms you have. The empirical formula tells you the simplest ratio in which they appear. Here's another example. This is propene. This has a molecular formula of C3H6. Here's another alkene. This is 1-pentene, C5H10. But they both share the same empirical formula. The number of hydrogens is double the number of carbons. The number of hydrogens is double the number of carbons. So they both share an empirical formula of CH2. So the molecular formula tells you how many atoms of the element you have. The empirical formula tells you what is the simplest ratio in which they appear. And that's the difference between molecular and empirical. Does anybody have any other questions based on this?
Just double check. For like Regents, like grams to convert decimals.
You will not have to convert, you will not have to calculate empirical formulas. Remember, convert to moles, divide by small, double if needed empirical. Not on the Regents. When they say determine the empirical formula, all you got to do is simplify the molecular formula, if it can be simplified. Review H plus donor and H plus acceptor. There are two definitions. There are two definitions of acids and bases. Arrhenius, they'll tell you by name. Arrhenius acids yield H plus or H3O plus as the only positive ion in solution. And Arrhenius bases yield OH minus as the only negative ion in solution. So again, to figure out which one is an acid or a base, all you got to do is look at table K for acids and table L for bases. That's nice and simple. As far as the one other theory, or a different theory, or another theory, or one theory, I won't call it Bronsted-Lowry. Anyway, acids are H plus or proton donors, and bases are H plus or proton acceptors. So for example, in the reaction HCl plus H2O forms H3O plus Cl minus. Is HCl donating or accepting an H plus as it turns into Cl minus? Accepting or donating? Donating. That makes it an acid. And is H2O donating or accepting an H as it becomes H3O? That would be your alternate theory base. So acids and bases are defined by Arrhenius by what ions they put into solution. The other theory, the Bronsted-Lowry theory, describes acids and bases in terms of what they actually do in a chemical reaction. What can be determined using electronegativity difference? H has an electronegativity of 2.2. Cl, 3. Let's try that again. This is also 2.2 because that's still H. Cl is 3.2. Na is 0.9. To find any of these, we simply refer to reference table S, which tells us the electronegativity. Hydrogen is 2.2, sodium is 0.9, chlorine is 3.2. It's all right there. Let's look at the electronegativity difference. What's the difference between the two hydrogens? 0 between the H and the Cl. And what about between the Na and the Cl? 2.3. The END tells us whether it's nonpolar covalent, polar covalent, or ionic. The general trend is 0 to 0.4 is nonpolar covalent, 0.5 to 1.7 is polar covalent, 1.7 and higher is ionic, 1.7 is what we call 50% ionic character. But a better way to tell is this. If you have two of the same nonmetal, it's nonpolar covalent. If you have two different nonmetals, most of the time it's going to be polar covalent. If you've got a metal and a nonmetal, it's always ionic. So you can use either what kind of element you have or the END to figure out your bond type. What are networks? Ugh. This is graphite. Graphite is made of pure carbon. Diamond is also made of pure carbon. Does this look like diamond? No. Does diamond do this? Yeah, nice piece of paper here, right? Can diamond do that? No, it's a good thing too. Graphite is a very soft, gray, metallic almost looking form of carbon. And in addition to that, it can conduct electricity. It's a good conductor of electricity. Because the way these are bonded is you've got thin sheets that are very weakly attracted to each other. And so they slop off, the sheets slop off each other real easy. Except apparently not off my hands. And they're not water soluble either. Yay! This is why if you get paper wet that's got pencil on it, it doesn't smear like it does with ink. Anyway, diamond is more like quartz. It's clear, got this nice crystalline structure, and instead of being made of thin sheets that are weakly attracted, every carbon atom in diamond and every silicon and oxygen atom in quartz is covalently bonded together. There are no weak points, there are no separate distinct molecules. There's just an enormous network of covalent bonds between the atoms. Network substances are extremely tough, very high melting point, as opposed to things that are not network bonded, which are softer. So soft, it'll slop off even on a piece of paper and you can draw with it. La 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 la. What is conserved in a chemical reaction? There are three laws of conservation: mass, energy, and charge. Those are what are conserved: mass, energy, and charge. When you balance, the masses have to be the same on both sides. When you balance, the charges have to be the same on both sides. And exothermic and endothermic are to balance energy in reactions. Mass, energy, and charge must be conserved. How to do decay problems. Let's suppose that we're going to do iron 53. Erase, 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 erase. Okay. 53 iron. And we want to know what it decays into. First, we need to know iron's atomic number, 26. Second, we need to know how iron 53 decays. And according to table N, it decays through positron decay. What's a positron? It's decay. Positron decay. There we go. 0, positive 1e. Now, the new particle that we get from this transmutation has the same mass, but what's the new atomic number? This is a positive one, not a negative one. 25. And then all we got to do is look up what element 25 is on the periodic table. Element 25 is manganese. And all decay problems work the same way. The last question, explain half-lives. The half-life of iron 53 is 8.51 minutes. Let's make that 8.5 minutes. Let's say we have 100 grams of it right now. In 8.5 minutes from now, we'll have 50 grams. 8.5 minutes further on, we'll have 25 grams. 8.5 minutes further on, we'll have 12.5 grams. So every time a half-life period elapses, we lose half of what we had at the end of the previous half-life. So it takes 3 half-lives of 8.5 minutes to get from 100 grams to 12.5 grams. If we have 12.5 grams now, 3 half-lives ago, we would have had 100 grams. So that's all you need to know about half-life. Every single time a half-life period goes by, You lose half of what you have, and it's turned into the other substance. So in other words, we don't lose 50 grams. Only 50 grams is still iron. The other 50 grams is turned into manganese. After the second half-life, we're down to 25 grams of iron and 75 grams of manganese. At the end of the third half-life, we have 12.5 grams of iron, and we have, what is that, 87.5 grams of manganese. So over time, this turns into that, and this is the half-life period with which it takes place. The difference between first ionization energy and electronegativity, and then they cheated, they put in a second question. So I will tear that off and put this one back into there. Okay. The difference between first ionization energy and electronegativity can be found on reference table S. Reference table S lists the first ionization energy and the electronegativity. What the heck are they? Atoms have positive nuclei with negative electrons orbiting around outside of them. And there's a natural attraction for the positive nucleus to the negative electron. When two atoms bond together, there's a competition for those electrons. So for example, when sodium bonds with chlorine, sodium has a configuration of 2-8s. Wrong. 2-8-7, chlorine, wrong again, 2-8-1, chlorine is 2-8-7. Sodium has 1 valence electron and chlorine has 7 valence electrons. Sodium's electronegativity, according to this, is 0.9. And chlorine's electronegativity is 3.2. Now what that means is that chlorine is more attracted to electrons than sodium is. And with a difference of 2.3 Gesundheit, chlorine has enough pull to remove sodium's electron completely and form an ionic bond, +1, -1. So electronegativity can be used to determine what kind of bond you're going to form. Ionization energy is, when you put sodium in chlorine, this reaction doesn't necessarily happen right away. We have to break old bonds. For example, chlorine is Cl2. We've got to break the bond between chlorine in order to make this reaction take place. Sodium atoms are held together through metallic bonding. So we have to add energy to break those metallic bonds. How much energy does it take to do this? Well, once we've got chlorine broken apart, chlorine has, like we said, 7 valence electrons. Sodium only has 1. We've got to get sodium to give up that electron. So you have to add ionization energy to make that happen. Sodium has an ionization energy of 496. Chlorine's is 1251. So when you heat up the mixture of sodium and chlorine, sodium is going to lose its electrons first, because sodium has a lower ionization energy than chlorine has. When you add enough heat to get sodium to cough up its electron, that's when the bond can form. So ionization energy is how much energy does it take for the metal to have its electron removed, and electronegativity is will the other element gain the electron once it's been lost. So electronegativity is an atom's attraction to electrons. Ionization energy is how much energy does it take to remove that electron. And that's the difference between them. And they're related. The stronger the electronegativity, the more energy it typically takes to remove it. Can you go over the conversion factors? Well, there's a lot of things that are conversion factors, but on the Regents, basically what they're going to ask you for is like, if you've got 60 grams, how many kilograms is that? And so we have to look up the common factors. 10 to the 0th for no prefix, 10 to the 3rd for kilo. And we know it's 10 to the 3rd for kilo because it tells us so on reference table C. Kilo is 10 to the 3rd. So there's 3 powers of 10 difference between that. That's 1,000. And we put the smaller unit over the bigger unit. There's 1,000 grams in a kilogram. Once you have your conversion factor, you take your given grams and cancel them out to get kilograms. The question is, do you multiply or divide to get rid of grams? In this case, what do we have to do? We have to divide, because multiplying will give us grams squared per kilogram. So if we want to cancel out grams and not get grams squared, we have to divide 0.060, and that would be decimal point, and that would be in kilograms. Now on the Regents, you can also do the old, move the decimal point over trick. If you got a multiple choice question, you want to do this, move the decimal point over, that's fine. Just make sure you're doing it the right way. Basically, you're going to divide if you want to convert to a bigger unit. You'll multiply if you want to convert to a smaller unit. That's pretty much all there is to it. Determine the number of total moles in hydrogen carbonate that we're... Ah, yes, I know this question well. I know this question very well, and many of you will probably recognize it as well. We had, I think this was citric acid plus sodium hydrogen carbonate, and it says if we have 0.01 moles of citric acid, how many moles of sodium hydrogen carbonate do we need? Do you guys remember this? Not everybody took that test, but those of you who did, yeah. Well, the numbers in front of a balanced equation represent the mole ratio. In other words, for every 1 mole of this, we're going to need 3 moles of that. If I had 2 moles of this, I'd need 3 times as much, or 6 moles of that. If I had 10 moles of this, I'd need 30 moles of that. So if I've got 0.01 moles of this, I'll need 0.03 moles of that, because it's a 1-to-3 ratio. So whatever this is, this will have to be 3 times as much. All right? You just have to remember that the coefficients, and if there isn't any, it's a 1, represent mole ratios. A 1-to-3 ratio. 0.01 to 0.03 ratio. Can you go over dipole, molecular, metallic, and hydrogen bonds? Okay. Only one of those is a type of bond, and that would be metallic bonds. There's no such thing as a dipole bond, no such thing as a molecular bond. There's only 3 kinds of bonds. Also, we've got dipole and hydrogen bonds. Those are attractive forces, and they wrote London dispersion but crossed it out. Those are attractive forces. And what's the only attractive force you need to know the name of? Hydrogen bond, right. H on one side, NO or F on the other. So let's take a look at the kinds of bonds you can have. We might get into it in more detail with a future question, so I'm just going to take a look at the basics for now. What kind of bond do you have when you bond a metal to a non-metal? Ionic. Metal loses electrons, non-metal gains them. They have opposite charges, they attract. What kind of bond do you get when it's just nonmetals, including hydrogen? Covalent, right. They're sharing electrons. Now, if they're sharing them evenly, an END of 0, like O2, it's non-polar covalent. If they're sharing them unevenly, like H and Cl, which have an END of 1, that would be a polar covalent bond. What kind of bond would you have between atoms of aluminum that hold aluminum atoms together to make a structural piece like this? What kind of bonds hold atoms of metal together? Metallic. And you can't form compounds with metallic bonds. But metallic bonds is what holds metal atoms together, allows them to conduct electricity, allows them to be shiny, allows them to be malleable, flattened into thin sheets, allows them to be ductile so you can make wires out of them. That's all down to the metallic bond. As far as the attractive forces are concerned, the way it works is this. Any molecule with a symmetrical charge distribution, in other words, the END is the electronegativity is the same on all sides, so that no side gets electrons out of any other. This would be a non-polar molecule, and it would have weak attractive forces. On the other hand, a polar molecule will take the same molecule and just put a chlorine in place of one of the hydrogens, has asymmetrical charge distribution. The chlorine is going to pull electrons more towards it than any other side, making the chlorine partially negative and the hydrogen partially positive. This would be a polar molecule, also known as a dipole. And this would have stronger intermolecular attractive forces. So nonpolar molecules have weak attractive forces, polar molecules have strong attractive forces. And that's really what it comes down to. And if on the end here, I put an F instead of Cl, if I had H on one side and or F on the other, now we're going to have some hydrogen bond action going on. And that's the strongest attractive force of all. How do you find the number of moles of reactant needed for a reaction with another reactant of X moles? That's related to the question we just went over with 0.01 and 0.03. Let me give you another example of it. Let's say we have N2 plus 3H2 forms 2NH3. Nice simple synthesis. And let's say I have 5.0 moles of H2, and I want to find out how many moles of NH3 that will give us. Well, let's see. It's a 3-to-2 ratio. 3-to-2 ratio between H2 and NH3. So I take 5.0 moles of H2, multiply it by that ratio. But I'm going to put H2 on the bottom so it cancels out. And I'll put NH3 on the top, so that's what I'm left for. H2 has a coefficient of 3, NH3 has a coefficient of 2. So 5 times 2 is 10, 10 divided by 3, 3.3 moles of NH3. You could very well be asked one of these stoichiometry questions. Now in class you had to convert grams and liters to moles first, and then when you were done convert moles to grams or liters. You will not have to do that on the Regents. You just have to use the mole ratio, moles at given to moles of target. And you want to cancel out your given so that you're left with target. And the numbers come from the balanced equations coefficients. Anybody have any questions about this? Just to simplify just a little bit, in some cases you don't even need to go through all of that. What if it said to make, let's say, 6 moles of H2, how many moles of N2 do we need? So we see it's a 1-to-3 ratio. It's a 1-to-3 ratio, it's easy. It's 1-to-3, which means that it's 3-to-1, which means it's 6-to-2. So that would be 2 moles of N2. So sometimes you don't even need to use the equation. Sometimes you do, sometimes you don't. As long as you remember the coefficients mean moles, and if there's no coefficient, then it's a 1. When light is emitted, oh good, from an electron going from the ground state, what does it show? Well, here's the deal. Every element has a nucleus, and every element's nuclear charge is different. So nuclei with 2 protons, like helium, have a nuclear charge of +2. Lithium's nucleus, +3. Beryllium's nucleus, +4. Now helium only has 1 energy level. This has 2 energy levels, but they're closer to the nucleus because the nuclear charge is greater. And the nuclear charge of this is even greater, so the energy levels are even closer to the nuclei. And that means when an electron falls from, let's say, the second to the first, it's going to give off a different amount of energy each time. So if it drops from second in helium down or second in this down, this isn't really to scale. This would be more like, like that, even closer. So what happens is, every time it drops an energy level, you're going to get light emitted of a different wavelength. This might be 720 nanometers, 700 nanometers, 680 nanometers for a wavelength. And that's the light that will be given off. Since every element has a different amount of energy and its energy levels, the patterns of light you get are different. And therefore you can use this light to identify what element you have. Do you remember the chart in the back of the room, the spectrum analysis chart, that you used to identify hydrogen and helium from the 2 spectrum tubes that we did in lab? So every element gives off a different energy of light, even if it's dropping from the same energy level to the same energy level. Going to the second to the first is different for every element. And so every element has a unique bright line spectrum. How do you know which valence electron has the most energy in the ground state? Okay, I think the question comes from a Regents question which gives you 4 different elements, and they say which element has electrons with the greatest amount of energy in the ground state. You can determine how much energy the valence electrons have by taking a look at how many energy levels that element has. For example, if we take a look at the elements in group 16 from oxygen to polonium, oxygen has electrons in the 2nd energy level, are its valence electrons, 3rd energy level for sulfur, 4th energy level for selenium, 5th for tellurium, and 6th for polonium. The higher those electrons are from the nucleus, the more energy they have. So polonium's valence electrons will have more energy than tellurium's valence electrons, which will have more energy than selenium's valence electrons, which will have more energy than sulfur's valence electrons, which has more energy than oxygen's valence electrons, which is why when electrons drop from high to low, the energy is lost in the form of light. So the higher the energy level is, the more energy it has. Just like jumping out of a 1st floor window, you might injure yourself a little. Jumping out of a 6th floor window, they might as well take out a knife and spread you on toast, because that's basically what you're going to be. The higher up you are, the more potential energy you have. Here's a question off a Regents exam. And this is a very common one that people miss that I went over one-on-one. At 101.3 kilopascals and 298 Kelvin, a sample of which compound absorbs the greatest amount of heat? I don't know. Let's look it up on table I. Now, the ones in question are NH4Cl, which absorbs, that's what the question says, it says absorbs, 14.78 kilojoules. Let's see if anything absorbs more than that. NaOH releases 44.51, so that's not it. NaCl absorbs 3.88. Well, that's less than 14.78, so NaCl doesn't beat NH4Cl. And LiBr also releases energy. So this not only absorbs energy, it absorbs more than the only other thing that absorbs energy. So the only way to get an answer if you're dealing with reactions or questions involving energy is to go right to reference table I, the most forgotten reference table on the reference tables. Okay, core table I feels so left out, and yet it's one of the most useful tables there is. Look at all those balanced reactions that you can look at. Look at how, oh, these are electrolytes. How do we know? We put them in water and they broke into ions. Very handy reference table to have. Weight average mass. Okay. Sometimes you'll come across a weight average mass question on the Regents. Often they'll ask you to show a correct numerical setup. Let's say we have a sample of X73 and X75, where this represents the atomic mass. And let's say that X73 makes up 80% of the sample and X75 makes up 20% of the sample. To get the weight average mass, we take 73 and we take 80% of that. To get for X75, we take 75 and we take 20% of that. And then we just add the two numbers together to get the weighted average. So it's 80% of 73 plus 20% of 75. Add them up and that's your weighted average. The other way you could write this is as follows. You could also write it as 73 times 80 and 75 times 20, but you got to divide it by 100 to convert it into a decimal. So it would be acceptable to write it in either format. Go over titration problem. Very good. Often they'll actually tell you it's titration as part of the question. And then you'll know, okay, that's when I start breaking out my MAVA equals MUPA. MAVA equals MUPA. So let's suppose that we have 50.0 milliliters of 0.10 molar KOH, and we have, let's say, I don't know, 30.0 milliliters of HCl, and we want to know what's the molarity of the HCl. So we take MAVA equals MUPA. We can use that directly because there's one H and one OH. So we can just use that. And so we're trying to solve for the molarity of the acid. So we divide by the volume of the acid and we plug it in. We put 0.10 molar times 50.0 milliliters over 30.0 milliliters. Milliliters cancel and you'll get your answer that way. Now the one thing you can't do is moles divided by liters. Many people will look at this question and use it when it says how many moles over liters. Can't do that because there's no moles here anywhere. Capital M doesn't stand for moles. Capital M stands for molarity, and that's moles divided by liters. So you can't use molarity equals moles per liter if you're going to do a MAVA equals MUPA problem. You can't do it. Got to use MAVA equals MUPA. Because MAVA equals MUPA, there are no moles. In fact, if you have moles, it's going to be abbreviated MOL, and that's as far as you can abbreviate mole. How can you tell if a reaction is spontaneous or not? Well, it depends. It depends on what kind of change you're talking about. If you're talking about enthalpy and entropy, what happens if I let go of this glass beaker? Which way does it go? So nature favors exothermic changes, right? A decrease in energy. And when this hits the table, what happens? Nature favors an increase in entropy. So how do we tell if it's an increase in entropy? Well, if we've got, let's say, Cl2 solid turns into Cl2 gas, what happens to entropy? Increases, right? Because solids have very little disorder. They're nice, neat, orderly, well-organized substances, whereas gases are chaotic. They're all over the place. So this would be an increase in entropy. So that would be spontaneous. You could also be talking about redox reactions, like a single replacement reaction. And for that, we have to use reference table J. And I'm glad we're doing this because we didn't do it with the other classes. If you've got a single replacement reaction, like let's say Mg plus zinc nitrate forms magnesium nitrate, 2 plus zinc. Or we could have zinc plus magnesium nitrate forms zinc nitrate plus magnesium. And we want to know which of these two is spontaneous. We've got magnesium and we've got zinc. Which one is more active? Magnesium or zinc? Which one is more active?
Magnesium.
Magnesium. That means magnesium can replace zinc, but zinc cannot replace magnesium. This reaction is not spontaneous, that one is. So you can use reference table J to figure out which single replacement reaction will be spontaneous also. La 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 la.